much for coming to this presentation. As Professor told you, my name is Patricio Olivares. The main goal of this presentation is trying to make a general description and a basic introduction to how we can apply and what are the interesting fields in the anomaly detection model system. So the idea here is trying to put that problem in context and trying to show you some applications and a few models that can be interesting for you and some tools that can be useful also for you. So that's the main focus of this presentation. So in order to give some context to this presentation, I will start talking about another kind of problem, that is the problem of fault detection. That means how we can detect when there is any error in our system, or you have a component broken, for example, in your enterprise or whatever you are working about. So when you are talking about fault detection, the idea here is trying to identify any malfunction on your system or any broken component, any deviation on the normal system, etc. And whenever you are trying to use fault detections in any of your system, the main benefit of using that, it will be that it will minimize any kind of negative impact in your system. Of course, if you are able to identify that there is any problem on your system, you can try to figure out why there is any problem and try to make some process to fix that. So whenever you are able to identify any failure in your system, you are trying also to improve your system and take some measures in order to avoid the problems from there. And of course, you will see in multiple parts, in multiple areas, that one way to try to solve that is just take people, normal people, use partial or complete human interaction with your system, and people will try to take a look in what are the possible problems that can be produced in your system. So in that sense, you will see, for example, in some system, people trying to look at several screens, trying to check the cameras that are looking if there's any problem of your system. That is very common, but we are probably agree that it's not a very useful or very efficient way to try to detect failures on any system. And of course, that will be costly because, of course, you have to pay those workers. Those workers are not working in other interesting areas on your enterprise. So you are wasting material there. So, of course, you can try to take some of those parts of the detection and try to automate that. And in that sense, of course, many of you are aware of the multiple machine learning models that right now exist. So, of course, you can try to take some of those models and try to make the automation, trying to make detections using those models. And of course, how you make detections on failures in any system, of course, will depend on your system itself. There are several different contexts on when you can try to translate these detections. But if you want to think in the most basic and in the most general pipeline to make this system works, you can think on something like this. In that sense, of course, any step that you are working here will depend on the context or your problem. But of course, you have to make a system representation. That means trying to check what are the problems that you are trying to identify and make sure that you are able to identify those problems. Once you are sure what are the problems you want to identify, you need to make data acquisition from that problems. Probably in most of the cases, that will be images, will be videos, will be maybe audio signals or any other kind of time series, for example. But you need to acquire that data, or any preprocessing that you need for that data is necessary also. Later, you will take those data and make any processing on them. And later, you can use a classification system. Why a classification system? You can translate any fault detection system in a classification system, if you think about it as the following, by classification models, the idea here is you can represent any fault detection model, fault detection problem as a classification of at least two classes. So the normal data will be one, and the failure data will be another. Of course, you can disaggregate this failure data class in multiple different classes, and you can extend this system in a multi-class problem. Okay, so that of course will depend on what are the failures that you are trying to detect on your system. And of course, if you are thinking this problem as a classification problem, you can use whatever models you are aware about classification. So of course, could be supervised model, unsupervised model, semi-supervised models, and that will depend on the nature of your data, on how many data you have available at the moment. Okay. This is a way to solve the system, and actually we'll show you some examples on how you can apply failure detection, this generic pipeline in any classification and failure detection problem. This is the idea here. So what examples of this? The first one is how you can use bidirectional signal from rotating machinery to detect if there is any failure in this component. So the idea here is trying to, with sensors, of course, trying to check what are the bidirectional signals that some components make. And later you can use an autoencoder, for example, a deep learning architecture of autoencoder. The idea here is trying to compress the data and capture the main features of the signal. And using that features, you can process that features as with any classification model that you want. So of course, in that sense, even the complexity of any of those parts, the idea of the pipeline that we discussed before is the same. You have a signal that you have to acquire, you have a processing and a classification process. Sorry for that. There you go. And later you can use a classification model in order to detect if there is any failure in your signals, in your data, and in this particular case, in the rotating machinery. Another example, in this case, this work that I'm showing here, they try to monitor the power unit from aircraft, the auxiliary power unit actually, and they use acoustic signals in order to make this failure detection. So the idea is almost the same. At first, they acquire acoustic data. Later, they try to check if the power unit is on or off. Okay, so that is at first a state classification. And later, they try to process this acoustic data in thermodynamic data in order to, using threshold, trying to check if there is any specific problem. In this case, it's not even a use of traditional machine learning models, but you can just check the principal features of your data, and using some threshold, you can check if there is any problem or not problem at all. Okay, so the idea here is you can use whatever you want to make this classification. Could be more traditional machine learning models, or could be using threshold models, or whatever you want to model that data in order to check any failure on your data. And the last example that I want to show you is this one. In that case, they are using infrared images in order to okay, so check the bevel gearboxes state and any failure that can produce from that. So once again, the idea here is trying to capture data. In this case, it will be the way to acquire the data will be using infrared images. Later, you have to pre-processing these images. In that case, they are using grayscale, taking a selection of what are the region of interest of your data. And in this case, because it's very expensive to acquire the data, they make an extension from a small number of label training samples. They extend all the data that they have available but unlabeled, so they have this extension. And using a simple hyperplane, they only try to make a threshold in between two classes that are the fault, the normal Bevel gearbox in this case. As you can see, whatever the problem you are trying to solve in this case, you can always think in this very basic pipeline. You acquire data, processing the data, later you use a classification model, two or more classes. Whatever the result is will take you what are the most common, the most probable failures in your system. But even though this is very useful, of course, in a lot of cases, there exists a very important limitation in this kind of system of fault detection itself. As you can see, fault detection models as classification model can be really easy because, as you can see, you can use any machine learning model that you are aware about. Even you can use threshold models. You are able to model your data. Whatever you want to use, you can use in this system. And if your model is good enough, probably your results will also be good enough. The problem here is that there is a big limitation, and the limitation is that you need data from your errors. And that's a problem because depend on what are the contexts that you are working about, probably the obtaining data from the errors will be expensive, or even in some cases could be impossible to acquire, or impossible to frequently acquire, frequently enough to train a machine learning model. So that's a really big problem. As you can see here, obtaining data from errors can be expensive, difficult, even impossible if failures are not frequently enough. So the question that we want to answer is even if we don't have enough data from our failures, can we do something about it? Can we identify a deviation of the normal behavior of our system, even if we don't have data from the errors? And the answer is yes, of course. That's why we are here. What are we using in that case is anomaly detection models. That is the principal goal of the anomaly detection model. So let's define at first what is an anomaly, how can we define an anomaly? And an anomaly can be defined as a deviation from the usual or expected behavior. In that sense, that could be, for example, a weird event in your system. It could be a misbehavior in any signal that you are trying to acquire. In a broken component, for example, will be a deviation from the expected shape of your components, for example. So it could be anything defined as a deviation of what you are usually expecting from your system. And anomaly detection models try to focus on detect when an anomaly is produced. Okay, so the idea here is how can we produce a system that is able to detect failures if we don't have data of our failures? And the idea here is the following one. An anomaly detection model tries to learn very well how the normal data looks like. If you are able to check how your normal data looks like, whenever you see anything weird, you can identify that as an error. And I mean error because not always will be an error, but will be something suspicious at least, and you can work from that point. So the idea here is trying to look how the normal data looks like and infer when there is something different from that normal data. And that is for that reason that anomaly detection models does not need any kind of data or any necessary data from the error itself. Okay. Of course, this idea has some advantages and disadvantages. Of course, if you don't need error data, that will be amazing because you can detect any kind of different errors without the error itself. But that will be less reliable as well. So you have to be aware about the limitations of anomaly detection. You can think, for example, if you have a system of components and all the data of your components are color red, for example. Maybe in some moment you will receive a new component that is color green. It's not an error, it's not a failure, it's just the same component but color green. If you are using images for your system, for your anomaly detection system, that will be a detection for your system because it's not the normal behavior. So that's what I mean when I say that it's not that reliable compared with fault detection, but it's more flexible because if you consider in that case that a green component is a failure, well, you will have that detection made. In that sense, let me show some few examples of how anomaly detection models work. Those are not that different from the pipeline that we checked before in the first part of the presentation, but the difference here is that you don't have any data from there. That's probably the biggest difference here. The first one is the fast flow model. That is an example of a group of models that is called normalizing flow model. And the idea here is as the following one. You will have a training data set defined as this one. And of course, this model can be represented as a probability distribution. Okay, that probability distribution will be defined as Px of x in that case. You can define whatever you want. And the idea here is trying to learn a representation from that initial probability distribution in order to map every single sample of your data in a new distribution. What kind of distribution? Well, any kind of distribution that is easily used for your anomaly detection process. The most common one, of course, will be the normal distribution. In that case, most of the time you will see in normalizing flow models that they use a normal distribution. But of course, if you want to change that distribution and you can try with another distribution, you can try also that. And the difference between fast flow and any other normalizing flow model is how they learn this map between the normal distribution, sorry, the original distribution of your data and the set that is the new distribution, the normal distribution. Okay. In that sense, what FastFlow make here is once again very similar to the pipeline that we checked before, but here once you have the extraction of features. You will have a deep learning network architecture that its only goal will be to make this learning of how to map any sample of your original data to this new distribution. So of course, the difference between different normalizing flow models will be this part here. Of course, you can change any other part, but most of the time you will have changed here in this part between different normalizing flow models. How you learn this new representation, this new map between the original distribution and the new distribution that you want to use. Another example that I want to show you is a model that is called PatchCore. This one is probably one of the most state-of-the-art models that you will see here. So it's very interesting to use this one because it's they have very good results when you use it, and actually it doesn't take so much resource when you are talking about computational resources. How this works? PatchCore is, of course, an image-based anomaly detection because it uses patches of the images. And the idea here is trying to take representation from different patches of your normal images, your original images, to create a memory bank that is called a memory bank. And whenever there is a new image, a new input image to your model, PatchCore will compare the patch of your new image to the memory bank that include the features that you learn from your training data that you have to remember is the normal data. So whenever you have a big distance, a far distance between the new sample and the training data, your memory bank, that will be checked as an anomaly in that sense. So, and it will produce an anomaly scores in that case. So the idea here is trying to, from the training data, create a memory bank of patches that you will have as a kind of database in your system. And you will try to, for any new sample, you will calculate an S score, that is the anomaly score here, for every single new X test image that you receive. And the idea here is take the new image, capture the patches from your image, and later capture the features for every single patch. And later you will calculate the distance between those patches and the patches from your memory bank. And how you calculate the distance is using the closest neighbors from every single patch. And the idea here is that this S factor depends on the calculation of all your distances between every single patch and your memory bank patch. And you will calculate the anomaly score as the feature that is, the maximum distance between those calculations that you make here. And also will be considered as a escalating number, because you want not only calculate this distance, but also you want to check what are the distance between those new patches compared with the distance for other patches. For example, if you are very close to a patch from your memory bank, but still this only patch is very far away from the other patches from the memory bank, that will be still considered as an anomaly in that sense. And here's how this works. So you will have some samples in the training process. You will have a pre-trained deep learning architecture here. So you can use whatever deep learning architecture with transfer learning in order to learn what are the features for every single patch. And you will have this represent as a memory bank that will be transposed here, and you will have this information as the features for the patches that you learn. And for every test sample, you will also learn the features for every single patch of your image. And we'll calculate the nearest neighbor with the neighbor set that we discuss later. Between those patches and the memory bank, and you will calculate the anomaly score. And of course, you have to decide a threshold in the sense that you have to select in what point you will check that as an anomaly or normal data. And the last model that I want to check with you is trying to check anomaly detection with autoencoders. And the idea here is very simple. As you can see, the idea is using a deep learning autoencoder architecture. So you will have to compress the data with the encoder. And of course, you can use the decoder to decompress the data in that sense. And you will have a new representation, a compressed representation from the original data. And the idea here is if you train your autoencoder with only normal data, whenever you pass to the autoencoder weird data, probably the representation will be far away from the original one. So you, in that sense, have to learn with normal data, how to train the encoder, the decoder, of course. You will learn the new representation from your original data, and you can take the distance between your original data and the new representation, and that distance can be represented as an anomaly score. And of course, you can make a threshold once again. Whenever you pass that threshold, that will be considered as an anomaly. You can see here, this model calculates the error between the original data and the reconstructed one. If there's any error that is smaller than the input, is considered as normal data. Whenever you have a very small distance between the original data and the constructed one, that means that you have normal data, and otherwise the data is considered anomalous. And this is the architecture. As you can see, the important part here is that you will have the normal data, and you will have this architecture of encoder-decoder here, and you can take the distance between the original image and the constructed one using the decoder. In that sense, this particular research also use this architecture to simulate new anomalous data in order to check if the system is working. But this is the main architecture of your system, and you can check if there's any anomaly using that measure. So that are the models that I want to show you, but of course, one of the questions that you can have here is, okay, it seems interesting, anomaly detection. How can I start working in some anomaly detection models, or at least try to check how they work? And the first thing that you should use if you are working on anomaly detection is this dataset, because this dataset is the benchmarking dataset that is used for anomaly detection, the MBTech anomaly detection dataset. This dataset contains more than 5,000 of images and more than, there are exactly 15 different categories, including some objects, like, for example, bottles and screw, and some different textures as carpet and leather. And of course, for every single object, you have the ground truth about what are the parts that has anomaly and what is the normal data including there. And this is whenever you want to create, for example, a new anomaly detection model, this is the data that you should check in order to benchmark your system, your model. Of course, if you want to try and create an anomaly detection model from the scratch, of course you can. But I found this interesting library that is called Anomaly, and I think if there's any of you that want to start understanding and testing how these anomaly detection models work, it's a very interesting, very good tool to start working on it. Anomaly is a Python library that is used for benchmarking and developing, and even deploying some anomaly detection models. It's only image-based, so if you are searching for models that work, for example, for acoustic signals or any kind of sensor-based signals, probably it's not very helpful, but if you are looking for something that works with images, that is a very good, very robust library. Its license is Apache 2.0, so we can use it as an open source code almost. It uses PyTorch Lightning, so all the code is based on that. It's really, and I want to stress that enough, it's really easy to configure and test. So if you want to try several different models, you can really make it very fast. It's compatible with most of the custom datasets, include MBTech anomaly detection dataset, and supports a lot of different models, include the patch core that is one of the state-of-the-art models, but including some other models that you can check in the webpage of Anomaly, of course. And of course, whenever you are using a library to improve your work, there are some limitations. In that sense, of course, the first one and the most obvious is that only if you want to use any other model that is not included in the original model, probably it will take you some work because you will have to create your own code in order to complement what is made in Anomaly. And what I found, and there is no information from this limitation, is that Anomaly is only compatible at the time with only one GPU. So if you want to use this model for 2 or more GPUs at the same time, it's not possible at the time. It's not very well documented, that problem, but they are working on that, at least what I found. And as you can see, here are some scores from the models from Anomaly using this dataset that is the MBTech one. And as you can see, at least for the moment, the best model that I'm aware about, of course, is the patch core with this backbone to learn the features from the patches. And the average score is 0.976. So it's a pretty good score. I tried that in different datasets that are not the benchmarking dataset and still work pretty good depending on the context, of course, 0.8, 0.9, close to that. Of course, it will depend on the quality of your image in that case. And those are some examples of on how it looks the output of anomaly. In that case, for example, this one is a normal image from a cable that is called down. In that set, you can see this is the ground truth, so there is no any patch for anomaly behavior. And of course, it's represented in the same case using anomaly. And here you have a cable that has some problems here with the wires that are included there. And this is the ground truth of this problem that is represented here. And this is the output of one of the anomaly detection models. I think that this one I made it with padding. That is one of the few models that are included in this anomaly detection library. To finish this presentation, I want to give you some conclusions. Fault detection models, that was the beginning of this presentation. Of course, they are extremely useful, and you don't want to only use anomaly detection models if you have enough data from your errors. Anomaly detection models will be only a complement from what you are working if you are working in fault detection, okay? In that sense, they can automate the fault detection model. They can automate totally or partially the process of identifying different kind of problems on your system. But of course, as we already saw, a fault detection model have several limitations. In that sense, if there is not enough or null information about your failures, probably you will have some problems trying to use a fault detections model. In that sense, anomaly detections can be very helpful because they provide a set of techniques that can make you able to identify several problems, even if you don't have data from those errors. And of course, there is already multiple machine learnings. This anomaly detection is an active research area for the moment. And there are several machine learnings and deep learning models that are applying for anomaly detection process. And actually, the last few months, talk about that, the Anomaly library that we discussed before was including new models at the moment. So it's a very active research area. So it's better to check from time to time if there is any new model that can improve your anomaly detection process. And thank you for your attention. Hopefully this presentation will help for you. And of course the reference from my work. Thank you very much.
On a du temps pour des questions? Questions?
Yes.
I have several questions.
Okay, no worries.
So, is there any ways to try to use k-means or like contrastive learning because we do have imbalanced data sets?
Once again, sorry.
Yeah. Is there any works we try to use, like for example, k-means, like unsupervised learning techniques like k-means, or for example, contrastive learning loss, in order to maximize the inertia?
Yeah. For example, if you are thinking about, for example, k-means or any other clustering models, it can be considered, for example, as anomaly detection, but because you need a class that is defined as an error in order to interpret, even if you are not sure about the data. That will be in the sense of fault detection, but not in the anomaly detection itself, because the idea here is you are only aware of one group of data. It's not the same. For example, using k-means, you will have two different or more different group of data in your training, and you don't have that in the training of an anomaly detection model.
Yeah. And the second question is that what was the limitation that they lead to create patch code?
The limitation you mean in the model itself?
No, like in other models that they did researchers to create patch code. What's the benefit of using patch code?
The benefits, at least compared with other models, I didn't see any several limitations that I'm aware, at least of. Patch code actually is the model that I am using the most because it's a model that identify, at least in images, identify very well what are the parts that are weird in your image. I'm not really aware about any additional limitations. Of course, it's not a perfect model, but yeah.
I understand because, like, for example, some examples like carpet anomaly detection, for example, we use patches because we can't, like, for example, predict the saliency region. But for other examples, why not using saliency region instead of using like random patches from the input?
Okay. The idea of patches there in patch course probably is the point that could be there is limitation because how you decide how to make those patches, that's probably the biggest problem there. And sorry, I'm not aware how the way they decide the patches is considered as a limitation compared with other models. I'm not aware about that. But probably this is the point that you can improve, for example, the way that patch score works, deciding how the patches are obtained.
Okay.
Yeah, thank you. Yeah.
Well, if you go back to the slide where you're talking about patch, forgot the name, sorry. You were explaining the equation for it, and also, yeah, this one. Okay.
Oh, this one? No.
No.
The patch.
Yeah, this one here. Yeah. So right here, what we have is like we have like a memory bank, right?
Yeah.
And my question is more like, is that memory bank static? So essentially, we have X number of data, and that's the number of data that we will be using, or that memory bank can be dynamic. If it is dynamic, then we may have a problem with the algorithm because if the memory bank grows, then we have to redo the calculations on the number of data points that we have there. So that was essentially the question.
Yeah. In the research that is shown here, it's static at least. I'm not sure if the people that made this research explored the idea of trying to make it grow. It will depend on how quickly it will grow, probably because they don't save the image itself. They don't even save the parts of the image. They save the features that are identified in that patch.
Okay.
So probably it will grow if you keep going on that memory bank, but it's supposed not growing that fast because they only save features from that sense.
Okay, that's fine. Because otherwise we may arrive at the same problem that we have with algorithms such as KNN, for instance.
Yeah.
That's the more data grows, we have to recompute everything.
That's right. That's right. Yeah. Yeah.
Actually, I think for this specific problem, you can use, like, for example, online learning, where we give the model like training from any input.
What kind of model, sorry?
Like we don't train we don't use our model like static, but we leave it all for online training.
Well, yeah, of course, not having your model as an online training has several problems because your data will be updating from time to time, of course. Probably this was one of the first exploration that made in that sense this research group because it wasn't applied to an industry in that moment. Probably could be explored. I agree with you in that sense. An online training from the models can improve several things, but as it was discussed here, could be a problem for them because you have to recalculate from the model.
Any other questions?
Yes.
So for the fast flow, you use the normal distribution, multivariate normal distributions based on this distribution.
Yeah.
So if we have some skewed data, is there some models who are based on this skewed distributions?
Yeah, as I told, when you are talking about normalized flow, that's the most common distribution that you will find on any different models. It depends on the type of data that you are working. Probably there are some different distribution that will work better in that data. So yes, totally.
Because with skewed data, maybe the distance for the left side or one direction, it's not the same
That's
for
right.
the other directions.
That's right. Totally agree.
So maybe the mixture of models also just normal mixture may be a good solution.
Yeah, that's right. That's right. As we discussed, it will always depend on the data. So when you're working with anomaly detection model, there are several assumptions that you have to make because you don't know what are the errors actually. So you have to make those assumptions and hope for the best. Actually.
Have you considered using variational autoencoders or anything that is based on the Bayes essentially assumption? It's like a prior and then. I know you've mentioned that the autoencoder you need to try to map with a certain distribution of the inputs and with the decoder the outputs. But in this type of algorithm, especially with the Bayes one, you have the prior, which is essentially what you suppose.
Yeah.
But you have like an intermediate distribution that is actually, you have the prior that is it will model based on the data to find that PZ, which is essentially a distribution that resembles much more the input data compared to the prior, and then you can use that to now do the anomaly detection, because then that distribution will be learned and not just assumed.
That's right. That's right. They could use these kind of techniques to just learn whatever the distribution your data needs for the representation. Actually, that would be a very. I want to be you aware that this is a compilation of what is in the research of the anomaly. This is, of course, none of them is my research, especially. But that will be interesting to explore, of course. Yes. Yeah.
My question is a bit general. I would like to ask like a question about, for example, in these anomaly detection models, I know that some of them can be used in case scenarios like cybersecurity, where we actually need to do this in real time.
Yeah.
Especially, for example, in anomaly detection, incident response time. So are these, for example, algorithms that use deep learning, specifically, for example, autoencoders or other one, consider processing time? Because we have that real-time case scenarios are really needing these anomaly detection.
Yeah. Well, this presentation was a little bit more focused on image model based, yes. But yes, there exists a lot of different models that work with signals. Even for fault detection itself, if you are aware of what are the expected type of attacks that you will receive in any cybersecurity server in your system, you can just model those attacks and use this kind of this kind of model based on signals. Okay, so you will have, for example, the number of requests received in your server in a certain moment. There are several enterprises that work in that sense. For example, I don't remember the name, but it's similar to the VPN security enterprise that work in that sense, trying to identify if there is any unexpected behavior, how the requests are made, and yes, you can find that. No problem.
So probably a question for who ask what's next? Because I see that there is a lot of possibilities because there is not a lot of models available right now to these kind of problems. So based on your research, what do you think are possible contributions in the future to this kind of research?
Possible contributions probably make a more specific, more visible connection between the fault detection and anomaly detection. There are not so many works that explore the how to solve the limitations of both systems at the same time, probably. Because as we told you recently, the fault detection has its own advantage, anomaly detection has its own advantage. So if you can work with both of those systems at the same time on your process system, that will be interesting for explorer, because it of course will improve how the failure detection as a general topic will work.
Another aspect, the hot subject right now is transformers.
Yeah.
So transformers, is it something that you think can add in these kinds of models?
Well, of course, in any of those systems, you can be creative on the architecture you are using for learning features and so on. Yeah.
But you cannot add ChatGPT.
Yeah.
That's another one.
Yeah.
Okay. So I think we have some questions online. It's I think in the chat. Okay, we have a question here. I don't don't know if you can see it, we are preparing a database of road defects detection as an image-based model. The patch core concept is very interesting. In fact, we went into with the Euro model so far, and we think go now with the pictures with no defects, as they are 10 times more. What are the things to emphasize and stress on when preparing the data set and the model?
Okay. If you consider the benchmark data set that we saw here,
I think if you have to click the chat, probably we'll see the questions.
Here.
If you want to read the question, otherwise you have to share. I think it's not shared anymore.
Okay, here's the question. Yes, what I wanted to show, if you consider the benchmarking data, there is another thing to explore. If you consider the benchmarking data set that is this one, this is the most common that you will see on working on anomaly detection. And in that sense, this data set, for any picture that you see here, you have a very well enclosed taken picture, and you can see a lot of details in every single picture. That can be translated as a limitation also in the anomaly detection models. I tried that in different data sets that they don't have the similar quality compared with this one, and it kind of worked, but of course it worked in a less reliable way compared if you have this kind of clear and well-centered images. So if you have the possibility for your data set to have well-taken pictures, very close with high quality, of course, I will recommend that in order to prepare your data.
So the main thing is the quality of the picture.
Yeah. That will improve or decrease depending on your model.